Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh. So today we start with second topic in chapter 3, kinematics of rigid body in spatial motion. Okay, spatial meaning space, from the word space, and it is in three-dimensional plane, x, y, z, and xz. Okay, so in this case, we have three plane with three axes. So the lesson objective, after completing this topic, you should understand the types of motion of 3D mechanical system, and then know how to find the velocity and acceleration of certain point or link, and also know how to find the angular velocity and angular acceleration of a rigid body. So in 2D, we can see a lot of system, starting from the robotic system, from the crane, which move and rotate, many more. Okay, and at the top, top is also one of the 3D system. And then after that, you should be able to analyze and solve the problems dealing with the 3D rigid body. Okay, so that is our lesson objective. So before we go further, we need to know the reference frame used in spatial motion. Okay, just like in 2D, we will have the absolute frame and also the moving frame, fixed frame, and also moving frame. So in this 3D system, we call the fixed frame as a global frame. Different name but similar, or similar meaning. Fixed frame, global frame, or absolute frame. We can say we can use any one of it. Okay, but for 3D, normally we use a global reference frame. So that is the fixed frame. Therefore, all the position, velocity, and acceleration refer to this frame will has an absolute magnitude. So you must remember, anything that we refer to the global reference frame will has an absolute magnitude. Either it is a position, velocity, and acceleration. And the second is the moving frame, known as local reference frame. And since it is moving, whatever position, velocity, and acceleration refer to this frame will has a relative magnitude. So relative position, relative velocity, and relative acceleration. So we need to know where to put the global and local reference frame. Of course, the global reference frame must be on the static point, whereby the velocity equal to 0. So the global frame must be put on the static point. So from the problem given, you should point out where is the static point to put the global reference frame. So as long as the velocity v equal to 0, then you can use as a global reference frame. And local reference axis must be put on all the joints or hinge where a section rotates relative to other section. As long as there is a rotation, then you must put a local reference frame. This is because the angular velocity and the angular acceleration of different section is different from other section. Okay, because one they have the angular velocity, then the angular velocity will be different from the other section which moving with different omega and alpha. And sometimes the local reference frame might be at different orientation, meaning the axis is not co-linear. Then you must be careful. In that case, we need to put the different name for the local reference axis. Even at different orientation, the cross product must follow the right hand rule. So in this case, the right hand rule is very important. So when talking about the reference frame, either it is a global reference frame or local reference frame, you should be aware about the orientation. So from here, the first thing you should know that the arrangement of the axis X, Y, and Z must always be in counterclockwise. So X and Y and Z can be at any point, but once you put X here, after X must be Y and Z. So you cannot put X, Z, Y. In that case, it will not follow the right hand rule. If you have different unit vector, E, F, and G, as long as E is collinear, collinear meaning parallel, as long as E is parallel with X, then the unit vector of E is similar as unit vector of X. So meaning X plus E, you can direct plus or minus as long as the arrow is the same. So if the arrow is different, opposite, then one is the negative of the another. And therefore, E cross F also similar as X cross Y, producing Z, and E cross F producing G, G cross E producing F, F cross G producing E. And if you rotate clockwise, then we get the negative. E cross G, negative F, F cross E, negative G, G cross F, negative E. And in other case, the orientation is different. X, Y, Z, and the other axis also X, Y, Z, but in different orientation. So in this case, this Y is not same as this Y. So this problem might included in your test or in your final exam, just to test how good your understanding about the unit vector. So Z, this Z and this Z is different, even though it both are capital. So the only thing you need to check is either it is parallel or not. If it is not parallel, then this Z is different with this Z. This Y is different with this Y. But in this case, X is same. So this X is equal to this X. So capital Y not equal to small y, capital Z not equal to Z. Even both are capital, it will not be the same. But X is similar because it is in the parallel position and in the same direction. And if we using vector product right hand rule, small x cross small y will not be equal to Z. But y, small y cross Z will be equal to X. So this X and this X is similar. So that is the most important thing that you should understand when dealing with the unit vector. So this is another key point that you need to understand. So if you put Y, X, Z, then it is wrong. It will not follow the right hand rule. So be careful. So X, Y, Z can be in any position. This can be X, but once Z becomes X, then X becomes Y and Y becomes Z. So this is a sequence of X's in the counterclockwise direction. Okay, next we go to the types of spatial motion. So this is also the popular question for part A or CO1, PO1. Okay, in 2D, we have learned about three motion, rotation, translation, and general. So in 3D as well, the same motion is implied, but since it is a 2D, then it can also move in 2D plane. So we can separate, can move in 2D plane, 2D meaning either one, XY, XZ, or YZ, similar as the planar motion. And rotation, it can rotate about only one axis at a time, X, Y, or Z, also similar as in planar motion. But for the planar motion, the rotation axis only Z. But as long as it rotates only about one axis, then it is similar as in 2D motion. And it can also move in all three axes, X, Y, and Z. So the component of position, acceleration, and velocity can be in I, J, and K component. Then rotation about a point. So rotation about a point meaning it rotates in more than one axis. So rotation about a point, it might due to the ball joint, not a bearing. So if bearing can only move in one axis, can only rotate in one axis. The rotation about a point, meaning more than one axis, may be due to the ball joint. The top is one of the example that can rotate about more than one axis. And lastly, general motion, which is the combination of any two from the above, from 1 to 4. The types of spatial motion is similar to the 2D motion, but we just need to break down the movement in 2D and movement in 3D, and rotation about one axis and rotation about more than one axis, and lastly is the general motion. So from the 2D, you just expand translation into 2D and 3D, rotation into one axis and more than one axis, and then lastly general motion. So how the spatial motion can move? So this is the common thing that we can see, a crane. So in this case, this crane is loaded on the truck. So when this truck is moving, so we have the global reference axis anywhere outside of the truck body. But if the truck is not moving, then normally the reference axis will be on the center of gravity of the truck or at this rotation axis of this crane. So in this case, we can see that this truck can move only in XY plane on the surface. So there is a 2D motion. But the crane on the truck, since it can move with the truck in 2D motion, it can also rotate in the vertical axis, Z axis. So meaning this is the first local reference axis, because the crane can rotate about this. So in this case, we can put the similar orientation of X, Y, and Z. So from this first joint, so we can see that there is another boom section, another section which can move up and down in YZ plane or XZ plane. So this boom can move in three plane or three axis X, Y, Z and rotate about one axis, which is in this case is X. But remember that this boom can rotate also with the rotation of this cabin, meaning the total rotation of this boom is two axes, about the Z axis and about the X axis. So this boom will have two axes of rotation, or call it rotation about a point. And at the end of the boom, we can see that there is another boom which can be extended. But since there is no rotation, we can treat this C to D as only one rigid body because there is no rotation. But at point D, there is a hook that can move up and down, and this boom also can rotate in X axis and Z axis. So therefore, the motion of this hook is in 3D and rotation also in 3 axis. So that is what you need to do in analyzing the problem. So this is the global reference axis, and the others are local reference axis, which can move. This axis can move with the lorry. This axis can move with the rotation of the cabin and as well as the movement of the lorry. And this local axis can move with the lorry, can rotate with the rotation of the cabin and also rotation of the boom itself. And as I said before, all the things that refer to global axis is a absolute position. Okay, this is the example of the rotation about a point. So this top spinning in omega k at the vertical axis, omega j at the y-axis, and omega I at the x-axis. So it rotates in all three axes. So thank you.